This online tutorial is about hydrogen bond acidity and basicity, which is useful in the context of Lewis acid-base strength. Hydrogen bond is an intermolecular or intramolecular interaction of great importance for many chemical species, from small water molecules to large biological molecules like proteins and DNA. IUPAC, in its Gold Book version 2.3.3, introduces hydrogen bond as follows: a form of association between an electronegative atom and a hydrogen atom attached to a second relatively electronegative atom. It is best considered as an electrostatic interaction heightened by the small size of hydrogen, which permits the proximity of the interacting dipoles or charges. Both electronegative atoms are usually, but not necessarily, from the top row of the periodic table, i.e. nitrogen, oxygen, and fluorine. Hydrogen bonds may be intermolecular or intramolecular. With a few exceptions, usually involving fluorine, the association energies are 20 to 25 kilojoules per mole or 5 to 6 kilocalories per mole. In addition, in another entry, as hydrogen bond in theoretical organic chemistry, IUPAC introduces hydrogen bond as follows: a particular type of multi-center, free center for electron, XHY, in which the central hydrogen atom covalently linked to an electronegative atom, carbon, nitrogen, oxygen, sulfur, forms an additional weaker bond with atom Y, nitrogen, oxygen, sulfur, in the direction of its lone electron pair orbital. The energy of hydrogen bond, which is usually in the range of 3 to 15 kilocalories per mole or 12 to 65 kilojoules per mole, results from the electrostatic interaction and also the orbital interaction between the antibonding molecular orbital of XH and non-bonding molecular orbital of Y. So in this way, IUPAC describes hydrogen bond in its Gold Book. We see that the general form of the hydrogen bond can be written like this, where these three dots represent the hydrogen bond between this hydrogen and this Y atom. In a narrow view, X and Y are small and electronegative atoms, nitrogen, oxygen, and fluorine. In a broader view, in addition to oxygen, nitrogen, and fluorine, X and Y can also be other atoms like sulfur, phosphorus, chlorine, and so on. From the point of view of electrostatic interactions, here hydrogen is partially positive as a result of attachment to the electronegative atom X or group X. And the partially positive hydrogen is attracted to the partially negative atom Y or an anion. In fact, it is attracted to the lone electron pair of Y as a region of negative charge. Based on this point of view, when positive charge on hydrogen or negative charge on Y increases, the strength of hydrogen bond increases. From the point of view of orbital interaction or covalent line interactions, here we have the orbital interaction between the anti-bonding molecular orbital of XH, sigma star, and non-bonding molecular orbital of Y, or simply its lone electron pair. In the direction of the lone electron pair, this angle is usually about 180 degrees. In this way, hydrogen bonds are like Lewis acid-base interactions. Based on any of these 2 points of view, Lewis bases, which are electron pair donors and have electron pairs to donate, are susceptible to form hydrogen bonds. Contributions of the electrostatic interaction and orbital interaction are a matter of debate. But presence of even a small amount of orbital interaction allows us to consider hydrogen bonds as a special type of Lewis acid-base interactions. In other words, hydrogen bond complexes like this are like Lewis adducts, at least partially. Indeed, many Lewis bases participate in hydrogen bond formation, and it can be considered as a general behavior of them. The general form of such reactions can be assumed as follows. XH plus Lewis base B yields the Lewis adduct XH B. Here, XH provides the hydrogen for formation of hydrogen bond. It is considered as hydrogen bond donor, abbreviated as HBD. On the other hand, the Lewis base B accepts that hydrogen to form hydrogen bond. It is considered as hydrogen bond acceptor, abbreviated as HBA. Based on the orbital interaction, from the point of view of Lewis acid-base interactions, XH hydrogen bond donor is an electron pair acceptor. It accepts the electron pair provided by B. So XH is a Lewis acid. On the other hand, hydrogen bond acceptor is an electron pair donor, and it is a Lewis base. Here it is good to mention that from the point of view of Pearson hard soft acid base concept, Lewis acids XH are a kind of hard Lewis acids, based on the simple observation that they form their stronger hydrogen bonds with fluorine, oxygen, and nitrogen, which can be assumed as hard Lewis bases. Similar to Lewis acidity and Lewis basicity, where Lewis acidity is the thermodynamic tendency or ability of a chemical species to act as a Lewis acid, that is to act as an electron pair acceptor, and Lewis basicity is the thermodynamic tendency or ability of a chemical species to act as a Lewis base, that is to act as an electron pair donor. We can also consider hydrogen bond acidity and hydrogen bond basicity. Hydrogen bond acidity is the tendency of a chemical species to act as a hydrogen bond donor. Hydrogen bond basicity is the tendency of a chemical species to act as a hydrogen bond acceptor. Similar to our previous discussions, we can consider quantities like equilibrium constants, enthalpies of reactions like these as a quantitative measure of hydrogen bond acidity or hydrogen bond basicity. In this regard, we can build scales of hydrogen bond acidities or hydrogen bond basicities. For a scale of hydrogen bond acidity, we deal with reactions like this between a series of hydrogen bond donors and a reference Lewis base, a reference hydrogen bond acceptor. And then values are hydrogen bond acidities of those hydrogen bond donors towards that reference hydrogen bond acceptor. In the case of a scale of hydrogen bond basicity, we deal with reactions like these for a series of Lewis bases, hydrogen bond acceptors, and a reference hydrogen bond donor, and obtained values are hydrogen bond basicities of those hydrogen bond acceptors, those Lewis bases towards that reference hydrogen bond acceptor, hydrogen bond donor. Such scales of hydrogen bond acidity or basicity are important, valuable, and useful in the context of Lewis acid-base strength. We can consider different reasons for this, like importance of hydrogen bond for many chemical species, evidences that orbital interactions like Lewis acid-base interactions are present in hydrogen bond formation. Participation of many Lewis bases in these reactions, and possibly more importantly, the fact that hydrogen bond acidities and basicities have proved themselves to be useful in analysis of Lewis acidities and basicities, or in general in analysis of Lewis acid-base behavior of chemical species. Indeed, in literature, there are many works and articles aimed to develop and improve hydrogen bond acidity scales or hydrogen bond basicity scales. Such scales, to be acceptable, should measure their associated quantities at the same conditions of the medium, solvent, and temperature. In addition, usefulness or popularity of such scales increase when the number of considered cases increase. Also, it can increase by increase of diversity of considered species, reliability and accuracy of measurements, domain of validity of the scale, and so on. So, parameters like number of considered cases, diversity of considered cases, accuracy and reliability of measurements, the domain of validity of the scale, and so on, show us how much a scale can be useful. The range of number of considered cases for hydrogen bond acidity or basicity scales range in literature from tens to hundreds to about 1,000 and even more, where there are few scales with several hundreds considered cases. Here, as an example, I'm gonna discuss for fluorophenol hydrogen bond basicity scale. In the book with the title Lewis Basicity and Affinity Scales, Data and Measurement, published by Wiley in 2010, Lawrence and Gall have devoted a chapter to hydrogen bond acidities and basicities. And they have discussed for fluorophenol hydrogen bond basicity as a promising scale in this regard. Lawrence, Berthold, and co-workers have obtained and gathered about 1,000 values for this scale. So it is a comprehensive scale of hydrogen bond basicity. In this scale, we deal with the reaction of Lewis bases, the hydrogen bond formation reaction of Lewis bases with this as the reference hydrogen bond donor. The general form of the reaction is as follows. For fluorophenol and the Lewis base react each other to form the related hydrogen bond complex. In carbon tetrachloride as the solvent at 298 Kelvin. The formation constant of this hydrogen bond complex is as follows. The concentration of these, here we represent as BHX, where BHX shows the basicity of B towards HX, where HX is the for fluorophenol, over concentration of B times concentration of HX, where HX is this for fluorophenol. Or we may consider the reciprocal of these as the dissociation constant. Therefore, fluorophenol hydrogen bond basicity represented as pKBHX is the negative decimal logarithm of Kb, or decimal logarithm of Kf. Due to the relationship between equilibrium constants and standard reaction Gibbs energies, we have this relationship between pKbHX and the standard reaction Gibbs energy of this reaction. So from values of pKbHx, we can also obtain values of the standard reaction Gibbs energies. Higher values of pKbHx equivalent to higher values of formation constants for hydrogen bond complexes show greater tendencies of Lewis bases toward for fluorophenol. Therefore, higher values of pKbHx correspond to higher hydrogen bond basicities of Lewis bases toward the reference hydrogen bond donor for fluorophenol. Lawrence and Gall have provided about 1,000 values of pKbHx in their book. They have considered different types of bases: oxygen bases, nitrogen bases, carbon pi bases, sulfur bases, halogen bases, and so on. Where, for example, by oxygen bases, we mean bases which use their oxygen atom to form hydrogen bond, and so on. In addition, for each of these families, they have considered subfamilies. For example, for oxygen bases, we have alcohols, phenols, ethers, aldehydes, ketones, esters, nitroalkanes, sulfates, sulfites, amine N oxides, amides, and so on. For nitrogen bases, we have amines, primary, secondary, tertiary amines, aromatic amines, nitriles, and so on. For halogen bases, we have fluoroalkanes, chloroalkanes, bromoalkanes, iodoalkanes, and so on. For sulfur bases, we have thiols, thioethers, disulfides, thioketones, and so on. So we see that we have a great number of values of pKbHx for diverse types of bases, and in this regard, this hydrogen bond basicity scale is a comprehensive scale. In addition, Lawrence and Gall in their book have discussed for fluorophenol affinity scale, which is the negative of the enthalpy change for this reaction. So, for fluorophenol affinity is the negative of the enthalpy change for this reaction. They have provided about 300 values for this scale. Here we have a very important question. Is this scale general? Or in other words, are the results of this scale, like relative order of hydrogen bond basicities or ranking of hydrogen bond basicities, applicable to other scales that use other hydrogen bond donors instead of this, or other solvents instead of this? From our previous discussions, we know that in general, we can't have a universal or unique order of Lewis acidities or basicities. This is also true for hydrogen bond acidities or basicities. But it's a great advantage for any scale to have its results applicable to other scales. In other words, when the generality of a scale increases, it becomes more useful. So, how can we test that a scale is general or not? To check and see if two scales are consistent with each other, are correlated with each other, one way is to see if their ranking, if their relative order of acidities or basities are the same. But a better method is to see if there exists any linear relationships between them. The general form of a linear relationship between two scales can be written as follows. Y is equal to mx plus b, where x here represents values of one scale, for example, scale 1, and y represents values of the other scale, for example, scale 2. M and B are constants. M constants which depend on the choice of scales. M is the slope and B is the intercept. If there exists any linear relationships between two scales, we can use statistical methods to obtain values of M and B, and also associated errors and standard deviations. Different types of parameters can be considered here. For example, we may search for a linear relationship between values of two pK scales. Its general form might be written like this. pKBHY is equal to M1 times pKBHX plus B1. This scale shows values of pK for basicity of B towards the reference hydrogen bond donor HX. While here, for this case, the reference hydrogen bond donor is HY. Instead of pKs, we may consider Gibbs energies. For example, this way. Or we may consider enthalpies. The affinity towards HY compared to the affinity towards HX. Also, types of quantities may be different. For example, like this. We may check to see if there exist any correlations between, for example, delta H and delta G for same or different hydrogen bond donors, and so on. It is good to mention this is a linear free energy relationship equation. Since it is a linear equation for free energies, it is abbreviated as LFER, linear free energy relationship. Since values of pK and delta G are linearly correlated with each other, these also are considered as LFER equations. So both of these equations are LFER equations. This is an example of linear enthalpy equation. If we can find linear relationships such as these between two escapes by using statistical methods, we can claim that two escapes are consistent with each other, or they are correlated with each other. Two escapes are well consistent with each other or strongly correlated with each other if such linear relationships for them have a small amount of errors or standard deviations. Okay, now the question is, do we have such linear relationships for fluorophenol hydrogen bond basicity scale? The answer is yes, but they are family dependent. Here, by family, we mean chemical species which are structurally similar. For example, all of them are oxygen bases, or maybe we are more specific. For example, we may only consider ethers, or we may only consider ketones, and so on. Consider these families. In the case of hydrogen bond donors, different hydrogen bond donors we might have. Consider OH donors like water, alcohols, phenols. Consider NH plus donors like trimethyl ammonium, CH3 taken 3 times, NH plus. Consider strong NH donors like amides, imides on one hand, and on the other hand consider VCH donors like CHCl3 chloroform, like one alkaline, like these alkalines, also weak NH donors like amines, anilines, pyrols, and so on. On the side of Lewis bases, consider these families: oxygen bases, sp hybridized, nitrogen bases like nitriles, RCN on one hand, and sp2 and sp3 nitrogen bases on another hand, like amines and so on. Based on values of pKbHx, we can see that for all bases like this. Please note that these families can be extended, of course. We can also add to these families other families. We can consider also other families. Based on values in tables, Lawrence and Gall in their book discussed that for all bases like this, the 4-fluorophenol hydrogen bond basicity scales and its results are applicable to other scales that use these hydrogen bond donors. On the other hand, only for these kinds of bases, the results of 4-fluorophenol hydrogen bond basicity scale are applicable to these kinds of hydrogen bond donors. So if a scale uses one of these hydrogen bond donors, it will be consistent with 4-fluorophenol scale for all of these kinds of bases. But if a scale uses the reference hydrogen bond donor, which is one of these ones, it will be consistent with 4-fluorophenol hydrogen bond basicity scale only for these type of Lewis bases. In other words, for oxygen and sp hybridized nitrogen bases, the results of 4-fluorophenol are applicable for most hydrogen bond donors, and on the other hand, for hydrogen bond donors of this family, the results of 4-fluorophenol hydrogen bond basicity are applicable to all bases. Due to such results, Lawrence and Gall in their book discussed that 4-fluorophenol hydrogen bond basicity scale is a reasonably general scale, and this is a great advantage for it. This example of 4-fluorophenol hydrogen bond basicity scale shows us what problems we may deal with when we consider scales of hydrogen bond acidities or basicities. This is the end of this online tutorial. I hope you find it useful.